proceed with the pre-processing pipeline or the Bmw pipeline in general. And I hope that we go on discussing in the background on Zoom and Discord. Please post your questions in Discord because you can copy all the information from the Zoom chat. And I would again like to point out that this is one pre-processing pipeline. And obviously there are a plethora of options how to pre-process your data. And every single step, every single notch that we turn here will change slightly the outcome. So from our perspective here at the Bmw, it is most important for open science that everything that we do is published openly, that we report simply. And if you decide that we want to remove channels manually, if you decide that we want to move time samples, so time domain cleaning manually, then that simply has to be reported. In that sense, it's objective because everybody can use that information and replicate what you have done with your pre-processing. But nonetheless, and as Mario already stated, we try to develop an automated approach so that we can work effectively with the data, which is not to say that you should not look at your data, of course, to learn what's going on, to learn from your experiments, to learn what kind of artifacts you can expect and see in different movement conditions, to basically become the expert for MoBI EEG, MoBI brain-body imaging. Having said that, the pipeline that we are showing here is the one that has been proven pretty successful over the last year for the majority of our MoBI brain-body imaging experiments. In that sense, we are very happy to have this kind of a pipeline that is semi-automated. A lot of options, obviously, to then again add manual steps, but we can do it more or less automatically to the ICA pre-processing and get very good results. But we're happy to learn more also from your side. So what your standard approaches are, I'm happy to see that we have this lively discussion. So with that, I would like to give the stage back to Marius.
Also, welcome back from my side. So, yeah, I definitely agree that the pipeline is just one of many, and definitely do not follow the pipeline blindly. I'll come to that in the very end. But that's also one of the reasons why there are many analytic plots that are generated if the pipeline is being run. So, so that you don't actually have to be blind when applying it, but you can actually see what it does to your data. Okay, so we had this discussion about, or we were at the topic of detecting and interpreting bad channels. We were almost done with this, but there's one thing that's missing, and that is that for this algorithm there is a problem actually. So I've been talking a lot about the algorithm and that we are using it and everything, but I have recently been brought or it has been brought to my attention that it's actually it's not stable. So there is this random sampling, and so far I had thought that this is done several times so that in the end it comes to a stable solution, but it's not the case. And it's especially a little weird because you only see different results when you restart MATLAB, because there is a little cache of the random sampling that is hidden inside MATLAB and only gets wiped when you restart it. So when you do the algorithm and do it again right away, you will get the same results. When you do the algorithm and do it again another day, when you restart MATLAB, you might get different results. And that's obviously a little unfortunate. It depends on datasets. Some datasets are super stable and it's not a problem, but other datasets can vary a lot. So there is a solution for this, also implemented in the pipeline. And this solution is that we do it iteratively. So the cache is wiped and we do it just once again. Ryan, yeah, that's actually a good point. Fixed seed number, yes and no. Obviously, this would lead to the same result, but it doesn't mean that it's a good result. It's just one random result with the same fixed seed all the time. So, so it's not actually it's better than not doing it at all, but it's not a solution that I favor, at least. Let's say like that. Yeah, so what we are doing is we do it iteratively, we do it several times, and then we check for every iteration. Here at the x-axis is the iteration, and the y-axis are the channels. So you can see these are 128 channels. This is the hands-on example data set that you should have access to. And if you run this, this part, you will get this plot. And you can see, okay, some channels are detected almost all the time, or definitely all the time. These are definitely bad channels, no problem. But other channels are detected only sometimes. And they are just below the threshold of, in this case, 0.5. Actually, I had other instances where this particular channel was detected finally as bad. So maybe even 10 iterations is not enough. If you really want to go sure, you might have 100 iterations. So for the hands-on session, that's not suitable because it takes too long, but just for your information. So you will see this plot, you will be able to judge for yourself whether or not it's fine as it is. But this is what you get. So I was surprised by that, that the algorithm is actually potentially very variable. Yeah, but this is done to improve this. And of course, you can select the number of iterations, and you can also select the fraction of detections that you need to flag a channel as bad in the end. So that's the badness, the overall badness, the fraction of how often it was selected. And by default, this is at 10 iterations and 0.5 as the fraction. That's definitely an improvement over not doing it at all. But as I said, you might even want to go further than that if you have more time. So that is this part. This is the finale of the bad channel detection. And now we go to the actual hands-on session, which was supposed to start right now, but I'll drop this for you so you can run this in the background, and of course ask questions in the chat and like on Discord. But yeah, so this is the code. This is line 64 in the code that you could download from the Google Drive. And as promised, there will be another poll, because I'm super interested how you actually clean your channels in your data analysis so far. And I'm also interested in your opinion, now that you've heard this, if you want to switch to the approach that is presented in the pipeline. 1 second to get the poll up. Beware of ransack. Yeah. It's a great algorithm. It can lead to great results, but it can also be problematic in this case. So yeah, this is the poll. The poll is up. Please answer if you like. And I'm curious to see these results.
So there's a specific question from Anna. If a channel is not marked as bad in one run, is it close to the cutoffs of the previous step? So, or rephrased, do those channels fluctuate around the cutoffs?
I'm not sure what the cutoff in this case means. The cutoff of the correlation threshold, like 0.8 in the original. Yeah, okay. I suppose so. So it probably is that, right? I mean, in the plot that I've showed here, every other option was switched off. So it could be that it fluctuates around the threshold, or it fluctuates around the time. So it could be that if you have something like 2 sessions that are each the same length, and the channel is only bad in 1 session, but you merge the 2 sessions and you have a fraction of 0.5, it could be that it's almost always detected as bad in one session, and then it's just around the time threshold. So that's also an option. Yeah, that's why. That's why you should definitely check the plots. There currently is no plot of the mean correlation or something like that. That's definitely an option. I will keep that in mind. That could be interesting to improve this even further. Yeah. So I'm looking at the poll here. Most people seem to be using clean raw data already, and for the people that do so, did you know about this not stable result? And if so, how did you deal with it? I'm really curious to hear about that, because this is it's kind of an interesting thing, right? Because the algorithm pretends to be replicable all the time, but it may not be. So if you in the paper just write that you select the data based on this algorithm, and you don't specify and you don't store in your data, in your script and so on, which channels exactly were removed, it might be that you never get your data back if you don't document this. So it's also one of the reasons why in the processing pipeline, the Bmw pipeline, every step is documented in the eeg.etc struct. Yeah. So there's a question by Balint. I was wondering why excluding channels which are bad sometimes, or even simply bad not all the time, if they work properly in 2/3 of the 2 to 3 trial segments epochs, they could be kept there and excluded only in segments where they do not give a good signal. What do you think? Yes, there is a toolbox for that. It's called trial by trial interpolation. It's also a toolbox in EEG Lab. I have this on my to-do list to implement that, but that is, let's say, that would be ideal, because it's not only the fact that you gain the signal, but you also keep the rank. Like you keep the rank of all channels that are not interpolated in all instances. So that would be perfect if this works, but I haven't tried it. Yeah, it's one of the things I want to do. Okay, I think let's continue. And here we are going now to the next part, which is the average reference. There has already been a discussion in the Discord about the question whether this is mandatory at the moment. And yes, this is mandatory. It's not skippable at this point. We only considered high density or at least high enough density EEG. It's a good point that we might want to consider giving there another option. I didn't think about that so far. But it's definitely something that we can consider in the future as an alternative to the average reference. But so far, this is mandatory. So why do we even do that? Just a little recap. We have the channel voltage. In this case, simulated channel voltage is always the electrode voltage minus the reference voltage. So that means the position of the reference does make a big difference. Wherever it is positioned on the skull, the signal will be lower, because everything that's close to the reference will have probably a lower signal than the rest that is further away. So in this case, the reference is positioned right there. So there's a virtual channel between these two channels that is the reference. And if we re-reference to the average, that would give us a more meaningful signal for the entire scalp. So this is the core idea of average referencing. There are other options, but for now, I won't discuss them, and they are not implemented in the pipeline. This doesn't mean that they never will be, but it's just at this point they are not. Okay, so there's one thing in addition. We do exclude the EOG, so the electrodes here at the eyes. We do exclude them for this, and you can declare EOG channels in the config file. And we do that because they don't behave statistically like EEG channels, and they would skew the point of yeah, the center of mass. That's the thing. Yeah, the center of mass. So yeah. All right, but there is a problem, and I've already mentioned that average referencing does cost 1 degree of freedom in your data rank. So that's, mathematically speaking, that's 1 rank of the matrix. But actually, that is not a problem if the reference was added back with zeros before. So if you take the reference and in that data matrix, there is a channel that is full of zeros, the rank stays intact. So you will get an additional channel. So instead of 128, you will have 129, but the rank will still be 128. As opposed to when you don't do that, you will have 128 channels, but the rank will be 127. Okay, so just one more visualization here. If this is the raw data, the simulated raw data to the left, and then we add a reference channel here at the bottom, it would be ideal if you could add it right there in between, but this is also how it's done in EEG lab. So it's just added, appended at the bottom. It doesn't matter if the location is correct. If it does have a correct physiological location, it doesn't matter which channel number it is. So that's fine. And then after this step, we do the re-referencing, and we can see that the channel that's here, you can see the way it fluctuates. It's somewhere here, and that's exactly where the reference was before. So that's the whole idea of the re-referencing with the channel added back to the data. Now, what if you don't know the reference? Maybe you have data where you don't know where the reference was placed, or it was placed in a position where you are just not interested in collecting the data or analyzing it at all, but you still want to keep the full rank. So what do you do then? You just ignore it. In the config file in the Bmw pipeline, you just enter no reference, and by default, we use the full rank average reference that was developed by Makoto Miyakoshi. It's a small glib plugin. It's like 5 lines of code, which essentially does adding the channel just like regularly, but it has one extra step. So as I said, it adds an empty new channels with zeros. It re-references to the average, so that's just the same as here, as before, and then it removes the excess channel again, so it's gone. So that means you do still have the correct average reference, if you will, and you still have the full rank, but you don't have the extra data. You don't have the extra channel. So this means that with 128 channels, without declaring a reference channel, you will still have 128 channels after the reference, and the rank will still be 128. So the rank is still intact, but the data is gone, as I said. So you cannot analyze this. Okay, and here we are done with the pre-processing actually. So now we are at the preprocessed.z file. This is what you get if you run the wrapper script. You will get this folder structure, and before we had the basic prepared set, that was this. And here we have the preprocessed.z, and there are also the interpolated channels. So there's a plot of the interpolated channels, which takes six 10-second segments of the data and plots them. And you also see the raw signal at these times, and you of course see the bad channel detection and which of these channels are interpolated then. Okay, so here we are. This was the pre-processing session. And now we switch to the next session, and I will do this without the break because there's a poll in a few minutes. Okay, so let's zoom in here, and we have the Eeg preprocessing that was happening there, and this is what's happening in the ICA processing. It's not just computing the ICA; it's filtering, then the ICA, dipole fitting, copying back to the unfiltered data, and then finally cleaning with IC label. But first, why do we do that? So I suppose most of you are familiar with ICA, but I will give a brief overview of why we do it and how it works in the very basic principles, right? So here we have a data set. This is 160 channels. Here at the bottom, you can see channels that were actually around the neck, right? Really not even on the scalp, it was a separate neck band. So that's a lot of channels. And then you probably all have seen these kind of plots already, some kind of topographies that ICA gives you in some way. And then if you look at the output of the ICA, if you look at the component level, you get this. In this case, you would get this. And then you can check, okay, this looks brainy and so on. I won't go into details here, but this is just a general approach. So that's why we use ICA. We want to look at components that we think are brain origin, and then only look at these and see the actual spectral properties. Side note, if you use a neckband channel like this, you get a very nice electrocardiography signal too. It's a component that is like a perfect ECG signal. Now, it's not always there, and it's not in all participants, but in many we get this. It's really cool. Just a side note. Yeah, so hands-on session. Again, we have this script. So it's the same script. You don't need to change anything or download anything. The script contains both the preprocessing and the ICA. As I said, it kind of belongs together. So that's why. This Amica is set up in a way that it has fewer iterations than normal. It's also commented as such. Beware, don't use these settings if you actually want to analyze your data with Amica. But for now, this is fine. And it takes a few minutes only. So there's another poll, as I said, and this poll will show up in the Discord. 1 second. So how do you actually use ICA? Do you only remove I components, which is probably the standard approach in seated experiments? Do you remove very clear artifact components like clearly I, clearly muscle, clearly other artifact components? Or do you remove everything that is not brain? So you keep only brain assays. Do you use it in another way? There are other ways, and please tell me if you do and what you're doing there. Or do you not use ICA at all? That's definitely also a possibility. Wonderful, thank you. So many people are answering. That's really cool. It looks like most people are removing clear artifacts. So anything that is unspecific, yeah, you keep, and anything that is clearly artifactual, you remove. That is really really nice and very interesting. Cool. Thank you so much for answering. And I think now we can continue for a bit, and you can let run Amica in the background, and I will just give a very brief overview of how Amica works. Just don't expect too much math, but just a principle approach, right? So most people, or at least I have heard this discussion several times, Amica seems to be some kind of dark magic. You throw data in and then you get brain out. So this is a little bit of a miracle sometimes, and I think it gives it a tad bit too much credit. It is definitely understandable, at least in the principle, not the algorithms like the Amica algorithm itself. I cannot tell you because it's also beyond my skills. But the principal idea behind it is definitely understandable. And So I will try to do that. So let's start with the sensor data. So this is the data that you record, right? So you have K sensors, in this case, 9. And these are labeled X1 to XK. And these sensor data, these are actually mixed data from many different sources. So if you have an electrode right there, it records signals from the front of your brain, from the back of your brain, which is transported to the electrode. It also records signals from the muscle and from the environment and whatever. So every single sensor is always a mix of different sources. And all that ICA does is basically trying to find ways to remix the data that you have, such that the remixing, the unmixing matrix is the inverse of the mixing matrix. So A is the mixing matrix, S are the sources, and X is are the sensors. So if you multiply the sources, the true sources, with the mixing matrix, you will get the sensor data. And now we try to get a unmixing matrix W, which is the inverse of the theoretical true mixing matrix. And then we try to estimate the true sources again by multiplying the sensor data with this unmixing matrix. That means that such a component is always just the sample of sensor 1 times the weight at sensor 1 for sensor 1 plus a sample at sensor 2 and so on. So this is really just everything that happens. It's just a multiplication of the data with an unmixing matrix. That's what ICA does. The key behind ICA is that it finds these weights in a way that they have a certain desired properties. In this case, it is statistical independence. So we try to find sources that have nothing to do with each other, so that they are at most separate from each other as possible. And then we have these weight vectors, or especially, to be precise, we have a matrix, and each column of this matrix is a vector. And this vector, these weight vectors, can be interpreted as a channel topography. So you can actually just plot these vectors using the topoplot function. It just really takes essentially a vector of numbers and the associated locations for these numbers, and then plots the picture. This is the topography that you get, the topography of the weight, or actually it's the inverse of that, but not so relevant at the moment. So this is how all this comes to be, right? And these components can then be interpreted as brain, eyes, muscle, heart, or other. So they kind of represent these sources. Ideally, they would compute the true sources, but this is not possible. It's a heuristical algorithm. There is no analytic solution. This is underspecified. The problem is underspecified. We have far more sources than what we have sensors. So this is never a perfect solution. And every ICA algorithm does it a little differently. So we have FASTICA, BINICA, InfoMax, ICA, and so on. And then we also have Amica, which is, as far as I am informed, the best working algorithm. So every algorithm uses some sort of the central limit theorem approach in one way or another. So the idea here is that the sum, or the mix, in the mixing matrix idea, the sum of distributions, in this case sources, is more normally distributed than the actual individual distributions themselves. So that's just a theorem, statistical theorem, and it can be used to find components that are not normally distributed, because that increases the chances that these components are actually distinct from each other if they are not normally distributed, but their mix is. And there's a little image in a two-dimensional way here by Arno on his ICA for Dummies website. Definitely recommend checking that out. And this is the principal idea here, that we have a data cloud, if you will, And it just turned and twisted in a way that in the end, the individual distributions are not normal anymore. They are in this case, uniformly distributed. That's also a side note, that's also why ICA is independent of the time. ICA really operates on clouds of points and has no idea whether one point was before the other or after and how far and so on. It's completely agnostic to the time domain. It's just checking for clouds. It has such lots of assumptions in that case. For example, it assumes stationarity of the sources. I will not go into detail on these here because in practice, they kind of work, even though they are almost in all cases violated, but it still kind of works. So now we are actually diving into this pipeline part, right? So we have the high-pass filtering as the very first part, and at this point, I would like to have another poll because this is just really super interesting to me. How do you high-pass filter the data before you compute ICA? This is interesting to me because it's actually the first paper I published was about this topic, and I'm just curious to learn how other people are doing it. This doesn't seem to work. I'm sorry, I don't know why, but the poll doesn't, maybe I have saved the wrong message to the bot. Trying one more time, otherwise we just skip it. Yeah, here we are. So you can tell me how you usually filter the data. And if you answer this poll, please keep in mind that actually EEG-Lab is a little tricky. EEG-Lab specifies the passband edge. So a filter is never a direct stop at a certain frequency. There's always a change, a gradual change from like having the signal until full attenuation. And minus 6 decibel attenuation is usually referred to as the cutoff. And the cutoff frequency is what defines a filter more appropriately in many cases than the passband edge. So in EEG-Lab, it is the passband edge. So you usually have to divide that by 2. If you are going too high, then it's actually another heuristic, but yeah. Okay, so most people use something of 0.5 or 0.5 to 1 Hertz. So yeah, so I think that's the default in many cases, also in the pipelines that you can see on websites or other papers. Many people use a 1 Hertz filter in EEG-Lab. So so that would be an 0.5 Hertz actual filter cutoff. This is very interesting, and in MoBI, this might not be appropriate. So I am trying to convince you that you will have to change this. First of all, why do we do that? Why do we do the filtering in the first place? Here are some plots from my paper from last year, where we were actually looking at the high-pass filter cutoff and the effect of the filter cutoff on the Amica decomposition in both stationary and mobile data. And what we found was that here the number of brain ICs in principle, as classified by IC label, coming here, increased with a higher high-pass filter. And in stationary data, that's the complete line, the full line, this was faster than in mobile data. So in mobile data, we needed a little bit higher filter to reach the maximum amount of ICs. What we also found was that the residual variance, some sort of physiological plausibility or brain quality of the data, I will come to that here in the dipole fitting, stayed more or less the same or even decreased. So that's good. So that means, taken together, that okay, yes, high-pass filtering before ICA improves the decomposition. That's not a surprise. Many people know that and do it. And this effect is stronger with more channels. So that's the darker green. And it is also more, you need a higher filter in mobile experiments. So this is very important because also in the MoBI community, people usually use the same filter cutoff, which I actually don't recommend. I recommend a higher one. So just to give you an additional overview, the effect on muscle ICs, eye ICs, and other ICs, so hard to classify, was also positive. So we got more of these muscle ICs, and at least in eye ICs, these were stable. Eye ICs are so clear that Amica just always finds them. It doesn't have anything to do with the filter in this case. And the number of unclassified ICs goes down, which is no surprise because the number of classified or well-classified ICs goes up. So that's nice, right? So this just tells us that we should use the filter. Okay, cool. Just one additional thing here is that this effect is really visible even in ERPs. So what we did here is we copied the ICA on unfiltered data. So the data that you will see here is not filtered with any filter. And here we removed all ICs that were not brain origin as classified by IC label. So that left us on average as an answer to Marzi's question, how many ICs we remove usually. So in this particular case, that left us on average like 15 brain ICs or something like that, 18 brain ICs. So not many. We removed like 90% of the components, something like that. And this improved the signal a lot, or measurable. And you can clearly see that both low, so red, and high, 4 Hertz filter are worse than having a filter in this area of around greenish 1 Hertz to 2 Hertz and so on. And you can also see that the green is a little lighter here in the stationary data than it is here in the mobile data. So we can definitely see that we do need a higher filter in the stationary in the mobile data than the stationary. And it has a visible, noticeable effect on the signal-to-noise ratio of your event-related potentials. Bear in mind that this is really unfiltered data, so it's really just spatially filtered, not on the frequency domain at all. So that was the high-pass filtering. And now we are switching to the actual Amica algorithm, in this case with the sample rejection. As a reminder, this is what gives you that. So you will get these kind of topographies if you run Amica. And as I've already explained the principle behind ICA, here is one additional thing that I want to tell you about Amica, because it has a sample rejection option. It has an automatic detection of bad samples that it then subsequently ignores when computing the topographies actually. And this looks like this. So this is the output you get in the console. And if we look at this here, this is doing the rejection. We see that the samples have a log likelihood. So the likelihood value should be high. It's always negative, so it should be less negative. Yeah, so that's that. Ideally, we have a likelihood value of, let's say, on average around -2 or something like that. But you can see that the minimum likelihood value here is -70-ish. So that's really bad. There are some samples where ICA is really super, it's more or less clear that these samples ICA cannot deal with, right? So the model, the ICA model doesn't work for these samples, and thus ICA will remove them. ICA just, Amica in this case, checks for more than 3 standard deviations below the average, and these samples will be removed. And then it does it again, right? So here we have the likelihood less than -3. These are removed. That's 3,000 data points. And there will be 9 more of these iterations. And in the next iteration, we see the values changed a lot. The average didn't change so much, just a bit, but the standard deviation definitely decreased. So in the next iteration, we have a definitely higher threshold for removal. And therefore, we remove 20,000 samples in this case. And then there are 8 more iterations afterwards. The number of iterations can, of course, be adjusted. And in the end, you will get a certain amount of removed data points. And these can be stored in the data which is happening in the eeg.etc struct in the Bmw Pipeline. And there's also a plot of removed samples, which looks more or less like this. So just to give you a little bit of an explanation, it looks more red than it actually is, because the red parts are painted over the green parts, and MATLAB can only paint at minimum 1 pixel. So so the red part is just overpainting the green parts, even though if you zoom in, it doesn't overpaint. It just adds that line. So yeah, this is what you get here, and you can look into the data. This is 10 channels, not the complete channels, otherwise it's just too large. 10 channels are plotted, and you can see the value should be something around 5%. Very clean data can be 2% even. Very noisy data can be 7 or something like that, but it shouldn't be so much more than that. Otherwise, you know something is weird. So yeah, 6.4% is already pretty much close to the upper edge. Okay, this is the Amica with the sample rejection. Side note, this sample rejection means that, in case you were wondering, we do not actually do time domain cleaning of our data in the pipeline. Because in our tests, so similar to the high-pass filter, I did a preliminary test comparing different time domain cleaning algorithms. And in these preliminary tests, which are unpublished and also not perfectly thought through yet, but in these tests, I found that Amica was actually best. So it just works best because it decides itself which are the channels that it cannot deal with, and we can trust that. So that's at least the state of knowledge I have right now. It might change in the future, but this is why we don't use any time domain cleaning. Also, no manual cleaning at all. No time domain cleaning other than Amica sample rejection. And these samples are not rejected actually from the data. These are just rejected from Amica. So so the data is still full, intact. It's just these are not accounted for when Amica computes its decomposition. Okay, so then we get this Amica file. So this is already, this is a big step because it takes quite a while to do that, depending on your data. It can take like literally hours or days. And you will get this amica.set file. You will also get the auto rejection figure and the plot of this. And you will also see the ICs, that like a plot of all topographies that we get. And here in this folder, you also see the output and all the variables that were used for ICA. So you can also check in the end what were the final values of some diagnostics and so on. So everything is saved and accessible on the disk. I see the question by Theo, is there a low-pass filter applied during acquisition? Depends on the amplifier. I think the Brain Products amplifier has like a 0.16 or 0.016 or something high pass, and other amplifiers are true direct current. Depends, yeah. So here, next step, we do fit dipoles to understand our topographies more. So recap, we have this topography, right? So this is what ICA gives us. And if we look at this, it looks very nice and smooth. In one area, it's very red, and in the rest, there are some nice and smooth lines around, and the rest is not red. It's green, or can even be blue. So this looks a little bit like that, and that's because it is. So this is a dipole, or a plot of a dipole, and essentially that's just what happens in the brain. So our neurons, our pyramidal neurons, are forming a straight line in our cortex, and when they fire together, we get a dipolar signal that is transferred to the skull, and that's what we measure with EEG, right? That's the origin of EEG. So here, here we have this little dipole. It can be very small, but due to the volume conduction, the way it spreads through the brain and the water around, like the water inside the brain, and then the skull and the skin and everything, the way it spreads, it gives a very large and smooth dipolar structure on the skull. So it's not pointy or something. And that's a nice brain source, right? If you get a topography like this, this is decent. It's actually not that great, but it's decent. Yeah. And importantly, this depends on the orientation or the exact origin. So it can be that topographies that look very, very different are actually from the same area. And I won't go into too many details about this because Anna will also later talk about that. But that's the reason why we do need the dipole fitting, because it could be that from the topography we just cannot really infer where was the origin of our independent component, right? Because we would like to know that if you want to know more about the brain and not just the scalp. So I won't go into too many details about the dipole fitting. I'm actually dealing with that in a short teaser that there could be some updates in the sometime soon future, which could be nice for MoBI. And if someone is very familiar with dipole fitting, please approach me in the chat. I'm curious to learn more about it. That in general, what we do here is we use the DipFit EEG Lab toolbox. It's part of the standard plugins. And we use a classical 4-layer boundary element model, or BEM, and that gives us this. So that's probably a plot that most of you have seen already if you were dealing with ICA and dipole fitting. This is just for every IC, we get a dipole and an orientation, so the little stick here, an orientation of that dipole. This is around the 1 to 2 centimeters accuracy. The location that we get here, this depends a lot, depends on the electrode location, whether they are subject specific. And of course, if you have a subject specific MRI of their brain, this is much better. But with all the standard stuff, there's that one guy, Colin, who got scanned a bazillion times, and we all use his brain in our models. And in that brain, we are usually in around 1 to 2 centimeter accuracy in that model, right? And what we get in addition to this, and that's also why DipFit is kind of interesting for us, is that we get a measure for physiological plausibility. It's called residual variance. So that's variance that isn't explained by the dipole. So you have this dipolar model, and if you, or let's go back here to this plot. The dipole model gives you a perfectly smooth topography on the scalp. The topography that we get from the ICA is never perfect. So So the difference between the topography that is explained by the dipole and the true topography, that's called residual variance. And that's a measure for physiological plausibility, so braininess, if you will, as also mentioned by or showed by Arnaud Delorme in the paper by in 2012. Okay, this is really important in our pipeline because, as I said, this is also more than just getting to know the ICs better and so on, because this gives us also an option to actually do brain imaging. So to go from the sensor level that we have around the scalp to infer what happens inside the brain and where exactly and so on. So this is really a powerful tool for us MoBI scientists. Now we have this, and we get the dip-fitted.set file. And this is here. This has the dipoles fitted. It's also depending on the data set. It can also take a while to fit dipoles. So that's why it's stored in extra. And the next point here is now that we copy the data to the unfiltered data. So that's the one after the pre-processing, not the high-pass filtered one. And here I don't have fancy pictures because it's really, there's one message, and that is, if you don't do that, then some measures can be distorted. So ERPs typically need filtering that is lower, so the threshold should be lower than what we need for ICA. And other measures can also be distorted, and therefore you should always copy the data back to the unfiltered data, so copy the ICA results back to the unfiltered data, and then only compute whatever you do. You can filter it again, no problem, but you shouldn't assume that the ICA filter suits whatever you want to do afterwards. And mathematically speaking, this is possible, just as a side note, because we did have this, this equation X, that's the sensor data, equals A, which is the mixing matrix, times S, the sources. And if we multiply this equation with the filtering matrix from the right, we would get X filtered, that is X times F, equals ASF, and that is A filtered, or A times the sources filtered. So essentially that means, mathematically speaking, A doesn't get touched by the filter itself. Of course, the content of A will change. That's why we do it after all. Otherwise, we wouldn't have to, or it wouldn't do anything. But mathematically speaking, you can copy this and just apply it again. There is nothing that speaks against it. It might distort if you overdo it, if you filter with a crazy crazy filter frequency, then it might distort the usefulness of the ICA, but it's still applicable, if you will. And I recommend checking out the actual book. It's the book about ICA by Hyvärinen. Yeah, just definitely check it out. And in addition, this is also necessary not only for ERPs, but also if we want to classify our components with IC label, because IC label was, I'm coming to that, was trained on unfiltered data. So therefore, this is problematic if we use it on filtered data. So here we are. We get the pre-processed and ICA.set file, and this is now in a next level folder. This is single subject EEG analysis. Here we have the pre-processed and ICA file. So this means that here, this is the data that we got from there, from this section, and it just has the information of ICA copied on there. So it's Amica is there, dipole fittings are there, and you can just apply them. But they are nothing is removed. It's just copied. So the information is there, and it's otherwise the state of the pre-processing. It's not raw, but it's also no ICA is, nothing is removed. It's just there. Okay. But then the next step is to remove stuff. And that's actually also the last step of this part of the pipeline. And that is cleaning these data with IC label. And here I have another poll. And that is how do you use an automatic classifier if you remove ICs, and if you do, which one? So here we are, the poll is up. Please add how you are usually doing it. I'm really curious. Oh, already many people are using IC label. That's great. It's a very young algorithm, actually. It's really cool. Right, Mara. I forgot Mara. Thank you. And I'm sorry. Yes, it exists. And I forgot it. So we seem to have a lot of IC level users, no users of Sassica, of OptiCAD, and also no faster users. And quite a good amount of people are doing manual classification. And then there is a larger group that uses classifiers and guides their own decision with this, which is probably a decent approach. And quite many people are also fighting with their colleagues over these decisions. So this is really a hot topic in the field, I would say, which ICs to remove and to keep and so on. And yeah, very nice to know. So definitely there seem to be people seem to be aware of IC level. That's good to know for me. I'm going to discuss it a little bit just to give you an overview what it does and how it works, and one or two quirks that we found. So IC label is an algorithm that is published very recently, created by Luca Piontonacini, and it classifies independent components into 7 categories, which are brain, eye, muscle, heart, line noise, channel noise, and other. In this case, you can see a wonderful brain component, which has 98.3% brain probability. Yeah, I would agree. This looks like brain, right? So in the background, this is a classifier that is based on a large data set of human classifications. It was like in 2016 or 17 or so. There was a continuous classification going on the website of the SCCN, where everyone contributed to classify these ICs. And this was then used to form the IC label classifier. And there are 2 algorithms that are being used by this. And one, the default one, the standard one, is the topographies. So they have a picture of the topographies and use that. And it also uses the spectrum of the IC, and autocorrelation as an additional feature. Something to mention here in the topographies, it actually has a picture. So it really plots the topography and then has a picture of a certain amount of pixels that is being used in the classifier. That means if you have topographies that are, for example, using electrode locations that are not in the standard layout, in the sense that maybe they are further below, like electrode locations here at the neck, that can weird the classifier out because then everything is shifted in the picture, everything is shifted a little bit to the top. And then the classifier has like another thing that's happening here at the bottom, which is where the neck is. And then that can be that the classifier doesn't really know what to do with that. So it's just a side note. And then there's a light classifier or light algorithm, which just disregards the autocorrelation. So they all only look at topographies and spectra and determine the braininess by that. And so we did tests on this. In our tests on our MoBI dataset, the default classifier was generally better in detecting brain ICs and only brain ICs. And it wasn't much better, just like a tiny bit. But it was really bad in detecting muscle ICs. So this was only one data set. I need to confirm this with more data sets. But please, if you use this and you found something similar, I'd be happy to know. Please tell me if you tried this and if you noticed something similar. In our case, we got horribly few muscle ICs. It was basically unusable to classify muscle in MoBI data. But the light classifier worked okay. So it's definitely not perfect, but it works okay for now. I won't go into details on the goodness or badness of the classifier because that's actually Anna's session. And so that's what you get in the end. And as I said, Anna will talk more about that. You have here the classifier, you have here the topographies, you have a probability for the class that it has for the majority of which won the vote, and if you click on the image here on the number, you can get a little bit more details about the signal. You can see the activity, you can see the actual probability, you can see the dipole location, the spectrum, and the continuous data right there. And there is something in addition. So this was just the IC label classification, like computation, but what we actually have is a wrapper that already uses IC label and removes certain ICs, and this can be either the classes. So you have to select the classes that you want. That can be only one class or many. So you can, for example, select brain and other, meaning these two are kept, and anything that is classified as muscle eye, heart, line noise, or channel noise is removed. Or in this case, as it is in the example data set, everything that is not brain is thrown out. And so here you select the class that you want to keep, and then there's the threshold, which is the summed score. Or if you have the classifier in the like at -1, the threshold here, then it is just checking the popularity vote. So that means every IC gets the class assigned which has the highest probability, and then every IC that has a class that is in the IC level classes range here is kept, and all others are thrown out. And if you have a range of between 0 and 1 in this IC level threshold here, then it checks the probability and keeps anything that is above a given probability here. And of course, it also plots the data in the end. And this is here code line 205 in the script that you already probably have open here and maybe already run. So so yeah, that's actually more or less the finishing line of what's happening, right? And in the end, you get this cleaned with ICA.set file in your folder here, cleaned with ICA. This is, as I said, if you run the complete pipeline wrapper, then you get this, and you get the brain dipoles, the figure for that. You get a figure for which ICs you were kept, and so you can see that in the end if you are happy with the results. So let's zoom out again. Here we are in the ICA part, but actually, as said, this large section here is kind of one. So I'm almost done here, but I want to mention this, right? So here we have the motion prep and the Eeg prep and ICA. Sane already talked about the motion prep, but I want to tell you something specific now, and that is I've mentioned that a few times already, but the Bmw pipeline comes with wrapper functions that will do the complete processing from raw Eeg and from raw motion to the processed one, right? And that's where this part comes into play. You can get these raw Eeg lab files, or you maybe have computed them when you followed the import session by Sane. And if you have these downloaded and you have the folder structure like this, and you have the scripts, these two scripts here, right, the Bmw config script and the example MoCap pipeline, then you can process the complete motion. And if you have the other scripts, that's the config script, these two config scripts are actually identical. And the example Bmw pipeline in this case, maybe I should have named it to example Eeg pipeline, but yeah, that's just it. And if you run these example pipelines, right, then you get the complete folder structure that I have already shown you here, right? You get all these files, and you can check all the plots in the end and so on. And this is also something that you can use in your data, right? So you can hopefully only adapt the config file, which should contain all relevant parameters if you follow the structure of the pipeline as I have presented it in the last 3 hours. So so that's pretty neat, right? You will get example plots and everything will run automatically. And you can adapt, of course, these parameters to whatever you think is more suitable. And then you start the script and then you just wait until it's done. And depending on your data set, it can literally take 2 weeks, but it will be done and everything will be automatic in the end. And you can see the plots if everything worked out to your liking. And here there would be the hands-on session for the config script. So you can now check out the config script. And in case some comments are unclear, everything should be commented. But in case some comments are unclear, please ask in the Discord. I am happy to take these questions and adapt the comments accordingly, because this is already public on the Git repository, and it is meant to be understandable by the comments alone. So if it is not, please just tell me. And then we have additionally this example Bmw pipeline, where we first run the config script. So we create the config, and then we run it for the complete participants. So we assume in this case that the data is already provided by the bits importer, and everything is loadable here at this part. And here you can see already the individual Eeg processing to remove non-experiment segments is also happening right there. After the loading of the raw data, I remove non-experiment segments. And then the wrapper functions are started. So check out this script, check out the config script, and tell me if anything is unclear. I'd love to hear that. Don't hesitate also to ask me later in Discord. Maybe you don't have time right now, but this is really dear to my heart. I hope that you find this useful and that it gives you value, and yeah, that you can use it.